Hello, it's Scott Manley here with Asteroid Update for October 2016. Now, in the first Asteroid Update, you might remember we were talking about the Philae lander and how it was being turned off. Well, now, 2 months later, the Rosetta mission has come to a proper end with the Rosetta spacecraft landing, or crashing more or less, on Comet 67P, Churyumov-Gerasimenko, and I have pronounced that correctly. The mission has, of course, been an amazing success for the European Space Agency, telling us all sorts of stuff about comets. And while many of you may not think of asteroids and comets as being similar, let me assure you that they have a great deal in common. Especially when they collide with other planets, it's hard to actually tell the difference. Also in the news in the last few days has been NASA's Scout system. Now, Scout is an automated computer program which essentially looks at data coming from the Minor Planet Center. Every new asteroid discovery, it's checking it to try and figure out whether it will come close to the Earth in the next few days. And if it does, it basically mobilizes a number of telescopes to collect more data on it so that the orbit can be determined with more accuracy. For example, on the 25th of October, a new asteroid was observed by the Pan-STARRS telescope in Maui, Hawaii, and within a few hours of the data appearing on the Minor Planet Center's website, it was assessed that this asteroid was going to pass within about 300,000 kilometers of the Earth a few days later, and so more data was collected. Now, sometimes these discoveries are expected to actually hit the Earth, and in this case it will be really useful because it will actually let us figure out exactly where these are going to happen. Again, while asteroids do hit the Earth every now and then, most of them are small blasts. It's the bigger ones that we're actually worried about. Okay, now an update on the competition. If you remember, every month we give away a number of t-shirts from the Asteroid Impact Mission, signed by rock star and astronomy legend Brian May. So we asked, what about asteroids inspires you the most? And we actually had two winners this month. The first is Game Dev Extreme, who said, I'm inspired by how asteroids could be a source of materials or the thing that destroys us. It all depends on us. And the second winner was Eric Marcel AB. He said that asteroids are the purest way we have to look at the past and the future of our home and the best creators and destroyers of life. So they both win. There's also a third place entry which was worth mentioning from 27 Callum S, who said, I think it's the number of asteroids that inspires me. Shows the vast distances of space, even in the asteroid belts, they are lonely. Okay, so we're going to have one last competition. This month we would like to ask you why you support the Asteroid Impact Mission. So get on Twitter and tell us why you support the Asteroid Impact Mission. Add the hashtag #ISupportAIM and we will pick the best answer and you will win a t-shirt signed by Brian May. But now, on to our special guest. Patrick Michel was actually in the previous episode. He was the expert that was answering your questions. He, however, is also one of the principal investigators of the Asteroid Impact Mission. So let's talk to him about this very important mission. And so today we have Patrick Michel. He is in Nice right now, but thanks to the magic of video conferencing, we have him on the show for us. Welcome! How are you?
Good, thank you.
So I guess everyone would like to know what you're up to in terms of asteroids. What would you like us to update us on?
Well, I'd like to update you on some space missions that are going on and some space missions that are in project. There are a lot of things currently going on with asteroids, which is great.
Yes, I know. That's why we have to keep updating people once a month.
Mm-hmm.
But we really like the AIM mission.
Mm-hmm. So the AIM mission is actually the European component of the IDA mission, which is a mission that aims at trying to make a test of the deflection of an asteroid. So in other words, we want to try and to check whether we are able to deflect an asteroid from its trajectory in case one dangerous comes on us.
Right, so to deflect it, you're going to hit it with a kinetic impactor, or rather a NASA mission will, in theory, hit it with a kinetic impactor.
Absolutely. In fact, we have two independent components. So one is the European component called AIM for Asteroid Impact Mission, which is simply an orbiter that is going to first characterize the target, because we need to know the enemy before fighting it. And then 6 months later, there is the projectile called DART, which will make an hypervelocity impact at about 6 kilometers per second on the asteroid. And the AIM orbiter will be there also to measure the deflection and to also measure the properties of the asteroid after the impact occurs.
Right, and so the target in this case has been very carefully chosen. Can you talk about this?
Yes, it's a very exciting target. Actually, it's a binary asteroid. So you have like the Earth and the Moon. So the Earth has a natural satellite, the Moon, and some asteroids also are double. So you have a big one and a smaller one, which serves as a natural satellite and goes around the other. And we have about 15% of the near-Earth object population, which is made of binary asteroids. So it's a non-negligible fraction of the population. And one advantage to go to a binary asteroid is that we can make the test of deflection without moving basically the body from its orbit around the sun. Because the problem is that when you make a test, you don't want to collide with an object and put it on a trajectory that goes onto Earth. So here what we're going to do is that we're going to shoot on the small satellite of the big body, and therefore we'll measure the deflection of the trajectory of the satellite around the big body, so that we don't really perturb the trajectory around the sun, but rather play on the orbit of the little body around the big one. And that way it's also better because this perturbation is faster than if we move an object around the sun, and therefore we can measure it almost instantaneously, both from the ground, from ground-based observatory, and from the AIM spacecraft.
So basically, it's it's holding it in place, and secondly, it's a lot easier to measure it relative to that larger body. So
exactly.
The asteroid is Didymos, and I hear that everyone has called the moon Didymoon. That's pretty cute.
It's unofficial
designation.
Name, but it's cute. I like it.
Well, I mean, how long does it take to actually name a moon of an asteroid? I don't know what the policy is on asteroid moons.
So that's the International Astronomical Union, which has a policy, and basically you need to have an image to resolve the small one. So in fact, the problem that we have, and that's what is fascinating in space missions, because each time we have a lot of surprises, is that we rarely have an image of a body before getting there. So for the main, the central body of Didymos, we have an image because it came close to Earth in 2003, and therefore we could observe it with radar observations. And with a radar observation, you can get a model of the body shape, and therefore a sort of image. It's not a direct image, but basically you can have a model of the shape. But for the small one, the secondary, Didymoon, we just know it's there. And we have an idea of its size, but that's all that we have. We don't know its shape, we don't know its surface and internal properties. And this actually applies to most of the asteroids. We don't have a lot of asteroids for which we have a real image, only the ones that have been visited by a spacecraft, and basically we have only 2 near-Earth objects that have been visited by a spacecraft, Eros by the NEAR mission in 2000-2001, and Itokawa by the Hayabusa mission in 2005. And the rest is just a light point in the sky. And therefore, that's why we are always surprised when we go there, because we don't really know what we're going to see. And this is one of the things that will happen also for Didymoon, is that we make some assumptions on the shape, but it will be when we'll be there that we will know exactly what it is made of. And that's why it's important to have the AIM mission, because the AIM component will be the first spacecraft to visit the binary asteroid, and in particular to understand what are the properties of a body which is as small as 150 meters, which is the size of Didymoon. And this is very important for us because so far we don't have any actual and real data on such a small body. So all our knowledge is based basically on the theoretical modeling. and they need to be verified by the spacecraft.
Right, we've never visited a body as small as Didymoon in space before. I mean, we have certainly been visited by smaller bodies as they've fallen to Earth, but there's a gap in our knowledge at this point.
Absolutely, so there are a few things which are interesting. First, we are going to deploy a lander. So AIM is actually a technology demonstration mission. It's not a science mission. So it serves as demonstrating a few technologies, and one is the deployment of a small lander of a body as small as 150 meters. And we have seen with Rosetta how challenging it is to deploy a lander on a body which is 4 kilometers, which is the size of the comet. Here, 150 meters means that the attraction of the surface is very, very, very small. To escape for the surface, you need only to be launched at a speed of 6 centimeters per second. So when I talk with you and I get excited on my chair, if I was on Didymoon, I don't come back on my chair. Yeah. So you see how sensitive everything is on the surface of such a small body. So this is the first demonstration, is the possibility to land on this surface. Then if we succeed with the landing, the lander will carry a low frequency radar. So basically, the aim of this radar is to probe the internal structure of the asteroid. And this would be the first time that we'll have direct measurement of the internal structure of an asteroid of any size. And therefore, we'll be able to determine whether this body is a monolith or whether it is an aggregate made of boulders with voids. And this is very important because we know that the impact response of a body highly depends on its internal structure. So if we want to be able to interpret the outcome of the dart impact, we need to know what is the internal structure. Otherwise, we won't know why the deflection will be such or such. So this is very important. And the same for the subsurface properties, so the first layers, which will be measured by the high-frequency radar on board A. So we have different ways to measure the internal properties of the bodies, and that will be the first time that this is done, and I would need an hour to explain you what are the implications in our understanding of the formation of the solar system, the formation of planets, and the collisional history in the solar system with this knowledge.
Right, I mean, so AIM is actually, it's like 3 or 4 spacecraft, I guess, because there's multiple CubeSats in there, right? And
absolutely.
And so it'll actually be viewing everything from multiple angles. So you'll, normally with a space probe, you have one probe looking at things. But having multiple points of view allows you to do things like radar tomography and you get internal structure and 3D in a way that's much, much more powerful than previous missions.
Exactly. I should already say that even if we just had a small camera on board, we would do a lot of science. Because as I said, we never visited a binary asteroid and we never had any image of a 150 meter body. So even if you just have a few images, that will be a revolution. And remember that for all the missions that just made a flyby of an asteroid, like Rosetta made 2 flybys, Near mission made 1, even with just an image, you had a cover of Science or other journals, because each time we learn something just by an image, because these bodies are totally counterintuitive for us, because the gravitational attraction is very different than the one on Earth. And therefore, even if the laws of physics are the same, the way they express is totally different, and the intuition is based on what we have on Earth. So each time we go there, anyway, we have surprises. So then, not only it will have a camera, but it will have, as you said, a low-frequency radar on board the lander, a high-frequency radar. So we'll have different ways to visualize the properties of the body. And in addition to that, we'll have CubeSats that will be deployed before the impact occurs. And one of the plans is to have the CubeSats be able to observe the impact at close proximity, because we can risk them with no problem. And therefore, follow exactly the impact event, while AIM will be placed at a few tens of kilometers from the asteroid in order to not get the ejecta into the spacecraft, and therefore with a lower resolution. So we'll have different ways to visualize how the body, the Didymoon, evolves around the central body, and how also it behaves when the impact occurs, which is very interesting.
So this sounds like an amazing mission, and as I said, this is Asteroid Update. We're all about the notion of protecting the Earth from the asteroid hazard. And this is really a mission which is facing this thing head on. That's one of the primary goals, is to analyze this.
Absolutely, and it's an international program because we have AIM by Europe, DART by US, and asteroid risk is an international problem. So it is very nice that we start to exercise with two of the main agencies together to build a mission toward the same goal, basically.
And so, assuming this is a success and we demonstrate the ability to divert an asteroid, we get some quantifiable result, we'll be able to sit back and relax a little, or
well, we
I think we have to keep looking for asteroids first, right?
Exactly, that's what I was going to say. I mean, we could relax, but in fact, there is still the goal of making the inventories of all the threatening objects, because we miss for the moment a major fraction actually of the bodies larger than 140 meters, which are the ones that can cause regional damages at least. We only have 15 or 20% of them, even less. So we need to make the inventory, because if you are able to check that you are able to deflect them, that's great. But then we need to determine who are the ones coming. And for the moment, we don't really know. But at least this mission will effectively serve to at least make sure that we have a technique that works. And also we learn from it, because regarding the impact physics, our modeling of the impact on an asteroid is only validated at laboratory scale on Earth. So basically we take hypervelocity gas guns, and we make impact on projectiles which have a size of a few centimeters. And we validate the numerical simulations with this kind of experiments. But now we are not sure that even if they are validated at small scale, everything is applicable at larger scale. So thanks to AIM and DART, we'll have the first fully documented impact experiment at asteroid scale. So at the very scale where we need to verify our models. And therefore, after that, when an object comes on our trajectory, at least we know that we can better design the mission, because our numerical models have been validated on one case.
Yeah, it gives us a way of predicting immediately right away, whether we need to come up with a new technology or just adapt the impact or technology we already have.
Exactly.
It's a small step, a link in the whole chain of discovery and mitigation, right?
It's a big step.
It's a big step, and
among the many.
Yes, but the mission has yet been to be funded.
So the reason why we are excited and also a little nervous is the fact that on the European side, the decision of to launch it will take place on the 2nd of December at what are called the ESA ministerials, where all the European delegates meet together and decide the various topics, which are basically linked to, for instance, the ISS, Ariane 6, but AIM is on the table. And the reason why we need the approval on the 2nd of December is because we want to be able to launch in 2020, because the impact has to occur in 2022. So it's a very short time to implement a mission in Europe. Actually, 4 years is very, very short. That's why we need it now. And the reason why we want to make the impact in 2022 is because we want to be able to observe the impact both from AIM, but also from the radar observatory on Earth. And in 2022, Didymos is coming at only a few tens of millions of kilometers from Earth, which is very close astronomically. And at this distance, the deflection can be measured from the ground. If we do it later, we can still do the mission, because AIM and DART can fly together, but we won't be able to observe from the ground. And it's kind of interesting to have the possibility to observe from the ground for two reasons. One is if AIM is not launched or fails, we never know. And the second is that even if AIM is there, you can compare the observation from the ground and the observation from the satellite, and therefore we can do what we call the ground truth. So you can compare and recalibrate if necessary and be able to better understand the link between remote observation from the ground and the actual data taken in situ.
So yeah, that's great, and I hope you guys have a great Christmas surprise because it'd be very best Christmas present for you guys, right?
Absolutely. Yeah.
And so yeah, thanks very much for turning up to the show. It was fascinating stuff, and I mean, you always are doing fascinating stuff.
Yeah.
And we hope to have you back on Asteroid Update in the future. But thank you very much, Patrick.
Thank you, Leo. I'm always excited to talk about this fascinating subject.
Yes, I am always excited as well. Thank you. Fly safe.
Thank you.
So there you have it, another interesting interview with one of the people working hard in asteroid science. We hope their review goes well, and of course, we'd want you guys to get your competition entries in for next month. We will, of course, be back then with another episode of Asteroid Update. Until then, I'm Scott Manley. Fly safe.